Good afternoon, everybody. Welcome to Lecture 31. We're talking about shock waves today. Hope everybody's doing well. I know you're all super busy trying to wrap up stuff in the last week before many of you are leaving campus. So let's get to it. All right, so today we're talking about shock waves. It's section 11.5. On Wednesday, we're going to talk about compressible flow in a duct with a changing area. We're skipping over section 11.6 to go straight to section 11.7 on Wednesday. And that is the last topic that you're going to be responsible for in this course, 11.7. All right, so if you remember from last time, we talked about how in a compressible flow, if you have a flow speed V that starts to approach the speed of sound, you can develop a shock wave, right? So here we have this red asterisk. It's emitting sound once a second, a beep. That sound is spreading out spherically. Here on the top left, it's not moving. Here on the top right, it's moving, but with a speed V less than the speed of sound C in whatever the fluid is. On the bottom left, the speeds become equal. These pressure waves start to build up and develop a shock, a strong discontinuity in the fluid properties. And then if we're moving faster than the speed of sound, we're in a supersonic situation and we've got this cone-shaped Mach wave. And communication can't happen before and after the shock sound communication because sound can't propagate through that cone of silence, right? And we'll see more about that in a moment. And then here's some nice Schlering imaging of a series of shock waves that are being developed by these airfoils in an attempt to slow the flow down, okay? And these would be considered oblique shock waves, as you'll learn in a moment. But first, let's take a little bit of time to look at the phenomenon of sonic boom.
Humans have been fascinated with speed for ages. The history of human progress is one of ever-increasing velocity, and one of the most important achievements in this historical race was the breaking of the sound barrier. Not long after the first successful airplane flights, pilots were eager to push their planes to go faster and faster. But as they did so, increased turbulence and large forces on the plane prevented them from accelerating further. Some tried to circumvent the problem through risky dives, often with tragic results. Finally, in 1947, design improvements such as a movable horizontal stabilizer, the all-moving tail, allowed an American military pilot named Chuck Yeager to fly the Bell X-1 aircraft at 1,127 kilometers per hour, becoming the first person to break the sound barrier and travel faster than the speed of sound. The Bell X-1 was the first of many supersonic aircraft to follow, with later designs reaching speeds over Mach 3. Aircraft traveling at supersonic speed create a shock wave with a thunder-like noise known as a sonic boom, which can cause distress to people and animals below, or even damage buildings. For this reason, scientists around the world have been looking at sonic booms, trying to predict their path in the atmosphere, where they will land, and how loud they will be. To better understand how scientists study sonic booms, let's start with some basics of sound. Imagine throwing a small stone in a still pond. What do you see? The stone causes waves to travel in the water at the same speed in every direction. These circles that keep growing in radius are called wave fronts. Similarly, even though we cannot see it, a stationary sound source, like a home stereo, creates sound waves traveling outward. The speed of the waves depends on factors like the altitude and temperature of the air they move through. At sea level, sound travels at about 1,225 kilometers per hour. But instead of circles on a two-dimensional surface, the wave fronts are now concentric spheres, with the sound traveling along rays perpendicular to these waves. Now imagine a moving sound source, such as a train whistle. As the source keeps moving in a certain direction, the successive waves in front of it will become bunched closer together. This greater wave frequency is the cause of the famous Doppler effect, where approaching objects sound higher pitched. But as long as the source is moving slower than the sound waves themselves, they will remain nested within each other. It's when an object goes supersonic, moving faster than the sound it makes, that the picture changes dramatically. As it overtakes sound waves it has emitted while generating new ones from its current position, the waves are forced together, forming a Mach cone. No sound is heard as it approaches an observer because the object is traveling faster than the sound it produces. Only after the object has passed will the observer hear the sonic boom. Where the Mach cone meets the ground, it forms a hyperbola, leaving a trail known as the boom carpet as it travels forward. This makes it possible to determine the area affected by a sonic boom. What about figuring out how strong a sonic boom will be?
So here we're just going to skip ahead and skip over the part about measuring the sonic boom, but you're welcome to go back and watch that later. And I want to skip ahead to the part about animals using sonic booms in nature. It's pretty fascinating.
Time, supersonic flight over land remains prohibited. So are sonic booms a recent creation? Not exactly. While we try to find ways to silence them, a few other animals have been using sonic booms to their advantage. The gigantic Diplodocus may have been capable of cracking its tail faster than sound, at over 1,200 kilometers per hour, possibly to deter predators. Some types of shrimp can also create a similar shock wave underwater, stunning or even killing prey at a distance with just a snap of their oversized claw. So while we humans have made great progress in our relentless pursuit of speed, it turns out that nature was there first.
Not surprising, right? So the um, shrimp that they were talking about in that video is called a pistol shrimp, and it's a pretty amazing little creature. You can Google BBC pistol shrimp to find um, a short video about the pistol shrimp, and it's really quite impressive. They actually produce sonoluminescence when they snap their claws because of the differences in pressure. So it's really, really one of the most amazing phenomena in nature. All right. I'm going to switch over to the annotator. And we'll get going. So just one more note about this video I just showed. If you downloaded an earlier copy of the notes, the blank notes to annotate that I uploaded last night, it had a different video here. So just be aware. You might want to download the annotated notes as well. Okay, so what is a shock wave? It's extremely thin discontinuity in fluid properties, right? We just saw the video, and from the last couple of classes, we know that it's a buildup of infinitesimal strength pressure waves, all occurring at the same location. They pile up, and those small delta P, delta pressure, delta temperature, delta velocity, they add up to a really large step change in these fluid properties as you cross from the upstream location following the flow to the downstream location across the shock, right? So if we look at this schematic here, here's our shock. This is a normal shock wave, meaning it's oriented vertically. If we've got flow from left to right, so upstream of the shock, we've got some stagnation, pressure and temperature, some static pressure, static density, static temperature, and velocity. And then we've got our upstream Mach number, which must be greater than 1 in order for there to be a shock here, right? We pass through the shock, and now ignoring the stagnation properties, all of the thermodynamic properties increase except for the velocity. So when it goes through the shock, basically it slows the flow down, but then as a result of that, the pressure increases, temperature increases, and the density increases on the other side of the shock, right? And of course, because the flow has slowed down, the Mach number on the other side of the shock, on the downstream shock, is subsonic now, so it's less than 1. So just some classifications. You can have a stationary shock just fixed, to some reference frame, or it could be propagating. And then we talk about normal shocks. So vertical shocks, you'd usually see something like this developed in a symmetrical duct or channel or nozzle. Oblique shocks are straight shocks, right? So the shock itself is straight, has a straight edge, but it's at an angle to the flow direction. And then we can have curved shocks as well, where the shock itself, the shock face is curved. So now we're going to do what we do best, right? Derive equations that govern how these properties change as they pass through a normal shock wave, and that's what we'll be talking about today. So now consider a normal shock in a duct. This could be propagating, or it could be stationary in the duct. We're going to draw a small, infinitesimally thin control volume around it. It's so thin that it has no extent, and so there are no real contributions from viscous forces at the wall. That's not really because it's not realistic that they're there, it's just because the control volume is so short. It's negligibly long. One more thing to draw attention to is that we're going to call the upstream properties before the shock, we're going to label them with a subscript X. And then after the shock, we're going to label all these thermodynamic and flow quantities with a Y. Okay. So now we've got a control volume fixed to the shock, whether it's stationary or moving. And because the control volume has negligible thickness, the cross-sectional area upstream of the shock is the same as the cross-sectional area downstream, and so we'll just call that A. No need for a subscript X or Y. And then writing down the continuity equation, we've got rho X, so upstream density, upstream area, upstream uniform velocity is equal to downstream density, area, and uniform velocity. And this is equation 1154. All right, so from the ideal gas law, we know that rho is equal to P over RT. This is probably the equation that's rewritten and recopied most in our textbook, the ideal gas law. Now in this section, it's equation 1155. So knowing this, we can just rewrite the velocity as, well, the fundamental definition of the Mach number is V over C, flow velocity over the speed of sound in that fluid, right? But if we now rewrite C using square root of KRT, like we derived time before last in lecture 28, we get this expression for the velocity. And this is 1156 in your textbook. Now, if we take 54, which is just the continuity equation, and we substitute this new expression, 56, into 54, the continuity equation, we cancel out the area, ratio of specific heats, and the gas constant, we get the following expression. P sub x times the upstream Mach number over the square root of the temperature, the upstream temperature, is equal to the same thing on the other side, but with all subscripts y for the downstream. Or rearranging this, we can put it in terms of a Mach number ratio. And this is 1157 in your textbook. All right, so we've used the continuity equation so far. We've used the ideal gas law. What do you think comes next? If you think it's the linear momentum equation, you're right. So summing the forces in the x direction, we get rho y vy squared a minus rho x vx squared a. The only forces, as we discussed a moment ago, from pressure, because the control volume is so slim that there's no time for viscous forces to accrue. So writing this in terms of pressure forces, we've got px times a minus py times a is equal to the same right-hand side that we had before. Or now, using equation 48 from last time that put the Mach number squared in terms of rho b squared over kp, we can rewrite this as rho b squared is equal to kp. I'm just rewriting equation 48 now, is equal to kp Mach number squared. Using this now together with the momentum equation, we get px 1 plus k Mach number upstream squared equals py 1 plus k Mach number downstream squared, or rewriting this as a ratio of static pressures, ratio of downstream static pressure to upstream static pressure across a shock wave. We get this. And this is 1158. And now we've used the continuity, so conservation of mass. We used the ideal gas law. We've used conservation of linear momentum. Now we're using conservation of energy. So in the general form, we've got our heat flux in times our shaft work in is equal to the mass flux times the enthalpy downstream of the shock minus the enthalpy upstream plus Vy squared over 2 minus Vx squared over 2. But because the control volume has 0 thickness in the flow direction, there can't be heat transfer in, any appreciable heat transfer in, or any work done on the fluid. So Q dot equals Ws dot equals 0, and we have just the enthalpy and velocity terms left. But what we've just written down on both sides is just the definition of stagnation enthalpy. So we can write this in the following way. And this is 1159. Now, finally, if you remember the definition of enthalpy, and if you remember that we derived equation 11.9, which told us that H2 hat minus H1 hat equals CP T2 minus T1, right? So we've got this relationship between the temperature and the enthalpy. If we assume an ideal gas with a constant specific heat C sub P, then the equation above becomes simply this, that the stagnation temperature does not change across a normal shock. Okay, now that's pretty unusual because most of the thermodynamic properties do change across the shock. The stagnation temperature is one thing that does not change. All right, now substituting in 50, this is also from last time, into 60, and 50 was just our ratio of stagnation temperature to static temperature, so T naught over T that we derived in lecture 28, and it was given in terms of K and the Mach number. We have Ty plus K minus 1 over 2 MAY squared equals Tx times 1 plus K minus 1 over 2 MAX squared, or rearranging to put this in terms of a ratio, we now have an expression that tells us the ratio of static temperatures across a normal shock, right? The ratio of the downstream to upstream static temperature. Of course, you do need both Mach numbers to be able to calculate this. And this is 1161. So now the equations that we've derived 57, which is a ratio of Mach numbers downstream and upstream of the shock. We've derived 58, which is a ratio of pressure, static pressure, Py and Px. And we've just derived 61, right, which is a ratio of static temperature downstream and upstream of the shock. All those formulas, it's great that we have them, right? But they all contain both the upstream and downstream Mach number. We would really like to have it just in terms of the upstream Mach number because it makes the calculations a lot easier. So if we take 57, the ratio of Mach numbers, that equation, and square it, we get the following result. We then sub 58 into 61 into the right-hand side, and we get a quadratic equation. And this quadratic equation has two solutions. So I'm going to box these. The first one looks a little bit trivial. It just tells us that the downstream shock number squared is equal to the upstream shock number squared. And that's the trivial solution. This is equation 1162. But this is the no shock solution, right? So we can have this situation. It just means that there's no normal shock wave, right? There's no discontinuity of thermodynamic properties before and after what we suspect might be a shock wave. So we'll call this the no shock solution. And then the other solution of the quadratic equation is a bit more complex. It also gives us MAY squared, and it tells us that's equal to MAX squared plus 2 over K minus 1 all over 2K times, or pardon me, over divided by K minus 1 close square bracket MAX squared minus 1. That's in the denominator. So we'll box that as well. And this is equation 1163, and this is we'll call it the shock solution, right? So when there is a shock present, this tells you the ratio of the downstream and upstream, or you can get the downstream Mach number from the upstream Mach number. All right, we're almost there. We want to do the same thing for other ratios, right? It's wonderful to have the ratios of these thermodynamic properties upstream and downstream of a shock, but it's much more useful if we have them just in terms of one Mach number, the upstream Mach number. So now we're going to go ahead and derive those other relations. So we're going to sub 62 and 63 into the pressure and temperature ratios that we derived, 58 and 61. If there is a shock, then those ratios are written as followed, right? We still have the quadratic equation that we're dealing with. 2k over k plus 1 times max squared minus k minus 1 over k plus 1. And this is 1164. And then the ratio of temperatures is similar but more complex. We've got three factors here. 1 plus k minus 1 over 2 times max squared. And then close parenthesis, open parenthesis, 2k over k minus 1, max squared minus 1. And then finally, open square parenthesis, k plus 1 in the denominator squared times max squared, close parenthesis. Okay, so boxing this one as well. These are our shock solutions. And then our no shock solutions. Unsurprisingly, are that Py over Px is equal to 1, and the same thing for the temperature, right? Ty over Tx is equal to 1, right? There's no discontinuity in the pressure and the temperature if there's no shock. All right. We got one more page, and then we'll look at an example. Does anybody have any questions so far? All right, so we basically just put a control volume around an infinitesimally thin normal shock, used conservation of mass, linear momentum, energy, and the ideal gas law, and we're deriving expressions for how the temperatures upstream of the shock relate to downstream of the shock. And now we're just finishing up with writing down some of those relationships for the stagnation quantities across the shock. We already know that the stagnation temperature doesn't change across the shock. What about the pressure? All right, so here just rewriting, just recopying equation 60 that we derived 2 slides ago. Just recopying it and boxing it. Just a reminder that the stagnation temperature does not change across a normal shock. And then to get a similar expression for the stagnation pressure across a normal shock, we use equation 51, and we end up with the following expression. So we've got our ratio of stagnation pressures. But it's in terms of both max and may, right? Both the upstream and downstream Mach number. Close curly bracket, k over k minus 1. All right, so we want to get this again in terms of just max. So we substitute in 64 and 63, and we end up with the following expression. It's a long one, but I have good news for you. We generally don't use these equations. We generally use the tables in Appendix D. as you're going to see in just a moment when we move on to our example. All right, so we've got here k plus 1 over 2 times max squared to the k over k minus 1 power times 1 plus k minus 1 over 2 max squared again, this time to the minus k over k minus 1 power times, this is the last one, 2k over k plus 1 max squared minus k minus 1 over k plus 1 raised to the minus 1 over k minus 1 power. Whew. All right, boxing that one. I'm boxing them. I'm not boxing them in red because although they are important, we don't tend to go to these equations and use them. Like I just said, we tend to use the tabulated values from these equations because they're so ugly and so awful to work with. And so, you know, most people would prefer to just use the tabular values and then just interpolate when necessary instead of plugging in and using these equations. All right, so this table shows the typical results of calculations made with these formulas with number 1162 through 67. And let's take a look at that. Right, so here we've got our nice normal shock. Upstream values have subscript x, downstream subscript y. So in the first column here, we've got just what our quantity is, right? So first row, we've got just our downstream Mach number. Then we've got our ratiostatic pressures in the second row. Third row, we've got ratiostatic temperatures. Then we've got ratio of stagnation temperatures, ratio of stagnation pressures, and then we've got a difference, an entropy difference across the shock. As you can imagine, going across that shock increases the entropy in the flow, right? So here, the second column, we've got our actual situation where we've got a shock wave. So our upstream Mach number is greater than 1. And then in the third column, we've got this hypothetical, not actually physically possible situation where our upstream Mach number is subsonic, right? If that happens, we can never have a shock wave. We need the Mach number to be 1 to have a shock wave, right? But in general, what we see, as we saw on the first slide today, is that the Mach number decreases because the velocity, which is actually not in this table, right? But as the flow goes through the shock, it slows way down and accelerates almost instantaneously, it decelerates almost instantaneously. So our downstream Mach number is subsonic. And all of the other thermodynamic properties, not the stagnation ones, but the static properties increase, right? So we have an increase in static pressure, increase in static temperature, and then the stagnation properties, temperature is constant, but the stagnation pressure decreases because we've lost some energy from the flow and it's gone into entropy instead. All right, it's time for an example. Are there any questions about the relationships that we derived today before we start on the example? Okay. So we've got a normal shock occurring in a stream of oxygen. The oxygen flows at a Mach number of 1.8. And the upstream pressure and temperature are 15 psia, absolute pounds per square inch, and 85 degrees Fahrenheit. So let's start by drawing a sketch of what we know. It doesn't say whether it's in a duct or not, so we'll just draw a stream and we'll sort of remain agnostic about whether it's in a duct. Here we've got our shock. And we know that the upstream pressure, Px, is 15 psia. We know that Tx, the static temperature, is 85 degrees F. And we know that the Mach number upstream is 1.8. Now, how did I know that that was the upstream Mach number, not the downstream? Because if we have a shock, before the shock, you have supersonic, right? Mach number greater than 1. after the shock, you have to have subsonic Mach number. So I know it's the upstream Mach number value, although it wasn't stated explicitly. Okay, we want to calculate static pressure, stagnation pressure, static temperature, stagnation temperature, static density, and velocity on the downstream side, so those Y values. We're going to use two tools, three tools really. We're going to use from, two of the tools are from Appendix D. One is table D.I for the isentropic flow. That we use when we're on the same side of the shock and we're trying to relate quantities. So here, for example, we're given the static pressure. We need to know the stagnation pressure. So we use the isentropic flow table for K equals 1.4. Then to relate quantities across the shock, we use table D.S. So that's the shock, normal shock table for K equals 1.4. Okay, so basically all those equations we just derived, people made a table for different Mach, for different upstream Mach numbers, and you can just go there and look up the table instead of using the ugly equations. The other thing we'll use once is the ideal gas law. Okay, so here we go. So T sub X is 85 degrees Fahrenheit. We, of course, need to convert that to Rankine, right? So we get 545 degrees Rankine for oxygen at standard conditions or at any conditions, as long as we can assume it's an ideal gas. We have that K is equal to 1.4. That comes from table 1.7. And then now we want to get some relationships on the upstream side of the shock wave. We want to relate, you know, the static to stagnation pressure. So now we go to table D.I, the isentropic flow table. Okay, from this table, we see that for an MAX of 1.8, we can write down the following. P over P naught equals 0.174. Now, the nice thing is that value, Mach number of 1.8, is given, so we don't have to interpolate for this problem. This gives us our stagnation pressure upstream of the shock, and it's 15 over 0.174. It is 86.2 psi. But we were not asked for that, so I won't underline it. But the other thing we get from table D.I is the ratio of static to stagnation temperature. And that is 0.607 at Mach number 1.8. So we can right away calculate our stagnation temperature upstream of the shock. It's 545 over 0.607, which gives us 897.9 degrees Rankine. Also not underlining that because that's not what they asked for. Okay, now we move on to table D sub S. Now this is the normal shock functions, the equations that we derived today. And this is also just for K equals 1.4. But we're basically, you know, K is 1.4 for oxygen. The K for air and oxygen is very, very similar for obvious reasons. Okay, now for a shock of 1.8, we can immediately pick off the table that MAY, the downstream Mach number, is 0.617. We can write down what the ratio of static pressures is. It's 3.613. we can write down what the ratio of static temperatures across the shock is. It's 1.532. And we can write down the ratio of stagnation pressures across the shock, and it is 0.813. All right, so now all we have to do is basically plug into these formulae. Just have to insert a new page here. Okay, so we just used table D sub S to get the relationships across the normal shock. We're now going to plug in using the values we found. So our downstream static pressure is 15 psia times 3.613, right? That's the number we just got from the table. So it's 54.2 psia. And this is one of the things they asked us for, so we'll go ahead and underline that. Our stagnation pressure downstream of the shock is 86.2 psia times 0.813, which is 70.1 psia. Our static temperature downstream of the shock is 545 degrees Rankine times 1.532, which gives us 834.9 degrees Rankine. And then finally, we know that our stagnation temperature is going to be the same. So it's 897.9 degrees Rankine. And our density, our downstream density, now we're going to use the ideal gas law. So it's the static pressure over RT. I want you to pay close attention, please, to the factor I'm going to use here, right? So I go ahead and just sub in that, 54.2, pardon me. That given 54.2 pounds per inch squared, but we've got to be careful about units, and it's not just converting from feet squared to inches squared. Look at what happens with our gas constant R. So if you look up the gas constant, you might get 1545 feet. It depends on what table you look at it in. You have to be careful about the units. So here we've got feet pounds per pound mole times degree Rankine, right? But to get all of our units to cancel, we've got to divide this by a 32 pound mass over pound mole. So just be careful about that. All right, and then times 834.9 degrees Rankine gives us, for our density, it gives us 0.194 pound mass per feet cubed. And then finally, last thing is the downstream velocity, Vy. Now, it's not tabulated what the downstream velocity is, but we can use the Mach number and the equation that we have for the speed of sound in an ideal gas, right? So we've got our downstream Mach number, and then we know that the speed of sound C is just KRTY. So we've got 0.617 times square root of 1.4, that's our K, times R. So again, we're doing that 1545 over 32 thing that we just did. times Ty, which is 834.9. And then we've got another 32.2 that we need to get the right units. And we end up with 831.7 feet per second. All right, so that's the example. So it's basically going back and forth. If you've got quantities that you're trying to relate on one side of the shock, say stagnation to static pressure or temperature or density, you use table D.I. If you're trying to relate quantities across the shock, you use table D.S. So I don't think we're going to do group work because we don't quite have the time, but I would like you to just try to find a value for the upstream stagnation pressure, P naught X, if the Mach number is now 3.6, right? So we're going to take just 2 minutes. It's 2:10 now, so we'll just work individually, not in groups, and go ahead and flip back to table D.I in your book and see if you can come up with a value for the stagnation pressure upstream of the shock if everything's the same, but now the Mach number is 3.6 instead of 1.8. And we'll check in 2 minutes. Of course, feel free to ask me along the way if you've got any questions. All right, so I don't know if you had time to really reach any conclusions, but let's take a quick check and see if anyone was able to successfully use table D.I to find the stagnation pressure. See, when I made the poll, I was going to ask for the upstream and downstream stagnation pressure, but we're a little shorter on time than I wanted to be, so you can still choose the correct answer by choosing the one with the correct upstream stagnation pressure. All right, so that's pretty good. So the leading answer is the correct one here. So I'm happy to see that. The correct answer is in fact, the first one. And I'll go ahead and put that poll result in the annotated slide so that you can see it and double check, but it's 1.3 kilopounds per square inch for the upstream stagnation pressure. All right, so just finishing up then. So a couple of things I want to note before we log off. are that midterm 2 extra credit has been assigned. So if you saw your midterm 2 grade go up, that's why. It was actually a significant effect. It brought the average up from 83 to 91. So I really thank everyone who, the couple of people who wrote to me and said, advocated for this approach instead. I really like the communication that I have with the students this semester, and I thank you guys. Last content lecture this Wednesday, the last thing that you'll be responsible for on midterm 3, it's continuing compressible flow, but then looking at flow through things like converging, diverging nozzles. Super fun topic. You can get things like flow speeding down when a nozzle converges, right? Which is counterintuitive. This week is the last week for Hyungan and his problem solving sessions and his office hours. So I really encourage you, if you're able, to take an early look at the homework and see if you have any questions. You'll still be able to email him even after the end of his official office hours. I have my office hour Monday morning. Feel free to sign up for a time slot, and you can of course email me as well. A reminder that your draft video projects presentations are due this Friday. It's just one single PowerPoint slide divided up into 4 quadrants with, the phenomenon you're trying to show, the equation, etc. You can see the more details in the guidelines. And then the homework and quiz are due after Thanksgiving break. So that's what I've got for today. Does anybody have any questions for me before we hang up?
We are going to take chapter 12 also.
What was the question? Sorry.
So we are going to cover chapter 12 after Thanksgiving.
So I have a poll for you. If you look at so we don't need to, we've met the course objectives. Okay. If you look at the extra credit assignment in this week, the first topic, there's actually a poll in there asking you guys whether you would like me to spend that final lecture Monday after the break on turbo machinery for fun, or if you'd like me to spend it reviewing for the midterm 3, right? So that's up to you guys. We've met our course objectives for turbo machinery, so it's really a question of what you guys want to do. All right, so be sure to take the poll. All right, thank you everyone. Have a great couple of days. I won't see you on Wednesday because I've got a doctor's appointment, but I will see you the Monday after Thanksgiving. Have a great break.